want to start us off with number one? Well, there's a typo. Okay, so let's look at the title of this section first. Modeling changing amplitude and midline. Okay, so when we were looking, just as a little side, if you go back to section 6.5 in your and I don't remember if that was like lesson 27 or 28, but if you go back, that was the first time we dealt with a spring. We compressed a spring. And we said when we compressed it, so we talked about it being at resting position, right? Here's our weight. And at resting position, that was our equilibrium or our midline. So we made that the x-axis, the resting position. And you all picked on me because I made the height of the spring when I compressed it, this part that's attached to the ceiling. Remember, I put it higher and you all gave me a hard time with that? All right. So then we compressed the spring 4 centimeters in that direction, and we let the spring go. When that happens, you go from your height, your highest point, you'll come back down through your equilibrium point. At some point, you're going to be here. And then you'll go down 4 centimeters below. You'll come back up, and then you'll come to that height again. So we modeled this. We started at the compressed. We can start, if we started here, that was our start time, it would have been a sine curve. If we start here at our maximum, then it was cosine. Just depends on where you start, all right? So what we really did, and this was just getting us used to modeling with sinusoidal, so this is a cosine with sinusoidal functions. Remember, when you say sinusoidal, it can be cosine or sine. And getting used to amplitudes and looking at real world phenomenon. But this is kind of a fake example. Well, not really. It's simple harmonic motion, which means you're not dealing with the idea of friction that can occur. Okay, so today we're going to be a lot more realistic than we were in the past, and that's where we're going today. So, and this includes animal populations. We've been looking at rabbits before, and the happy rabbits multiplying away. But we've been saying for the rabbit population, when we're saying that their population stayed static, the amount that were born and the amount that died off sort of equaled each other. So we had a nice sinusoidal function. So we're really going to examine behavior today that has this oscillation in it, but it's not going to be quite as unreal. It's going to really model what happens in behaviors in the real world or situations you might look at, whether that be in physics or you're an environmental ecologist and you're out looking at populations. Okay, these are more realistic than what we've been doing. Hint, suggestion, there's a little change in our models, okay? So, Leah, you want to read too? For those of you who want to know, this is your first example in your textbook. So those of you who want to, I think it's example 1 or 2. It's right there in your textbook. Let's say it's example 1 in text. So for those of you who want to sit back and relax and watch this develop, you could then go back and take notes right out of your textbook. And I'll try to tell you when there's a textbook example. Okay, sorry, Leah, go ahead. Okay, so first of all, we're seeing this idea of average, mean, average, and previously we didn't see that word average. So in terms of our sinusoidal functions, what represents the average? The midline. So this is just another way of talking about your 50 ALK above the midline and 50 ALK below. That's how the population is oscillating. Now back in 6.5, we never would have had more elk or rabbits or deer or whatever more than 2,000, right? That would have been our maximum. So something is changing here. What's changing? What's really different about this one? The midline, yes, is definitely changing. And how is the midline changing? The midline is the average number at ALK, right? Which if we say time t equals 0 right here is 2000, what's happening to that midline? It's going up by 4% each year. It's growing, okay? So what kind of function comes to your mind when you hear things growing at a rate of 4%? What kind of function? Exponential! Yay, Peter! All right, exponential. So one of the things we have to keep in mind is just some real basic ideas about exponential functions. So let's see, what do we know about exponential functions? It has a decay rate or a growth rate that's a constant percentage. So one model we could look at, just as a quick review, would be, in this case, since we're talking about a population, P sub naught, your initial population. We had all this way back in the beginning of 108, which might seem like 20 years ago when we reviewed exponential populations. 1 plus R, R being your constant growth rate or percentage or your constant decay percentage raised to the T. We also could represent this as P sub naught and their equivalent E to the RT if we use E as a base. Right now we'll stick with this first one. Later on we'll talk about E to the RT. Okay, so what do we know so far? We know our initial population is 2,000. Our value for R is always a percentage, so 4% is 0.04. So when I add 0.04 to 1, and I raise it to the power of T. So this is going to be called P of T. This should have been F of T up here. So let's just call that P of T. So this equals 2,000 times 1.04 to the T. So when time T equals 0, we put a 0 in here. Anything except for 0 to the 0 power is 1. There's our initial population, 2,000, right? So that's our midline. After 1 year, our midline is going up. It's moving to be 2,000 times 1.04, right? So it's going to be what, 2,080? And then the next year, it's 1.04 again times 2,080. So this midline is shifting on us, right? We have a shifting midline. All right. So the model that we need to create needs to deal with the fact that the average number of ALK, which we've been calling our midline, is growing each year. And then on top of that, the population's oscillating based on that midline. So we've got like two things we have to like kind of account for, right? It actually is fun when you think about it. All right. We know that we want to have our model. Here's the models we've been using in the past. What does A represent? Amplitude, right? B is our what? B is the period. 2 pi over P, B is the period, or 2 pi over P is B. B is your horizontal compression or stretch. Works the same way it did way back in Math 107. And then we have our midline that we add on there. So now our midline isn't just going to be 2,000. It's growing. So how's the midline changing? We've already discussed that it's changing exponentially. So the model for the midline, is going to be our initial population times 1.04 to the T. What did I say, or where? Well, you know, because I didn't see up here, I used P of T, and I didn't want you to confuse that with this P of T. Oh, I see. Yeah. This one could be a decreasing, like exponential growth and exponential decay. So they could just be different. You'll see in a minute. Okay. All right. So where I see midline, that's what I'm going to write. That will be my midline. So let's see if we can get a handle on this equation. We've got, now I don't even know yet if I'm going to use sine or cosine. Maybe this was just supposed to be a cosine here. Okay, midline. Could be either one. That's probably what I meant by or. All right. So P of T, well, we've got all this junk ahead of it, sine of BT, or maybe a cosine of BT. But our midline now, instead of just being 2000, is this changing midline, this growing midline. Okay, so we can fill in that much of our model. All right. What else do we know? We know the oscillation is 50 above and 50 below, right? This changing elk population, 50 above, 50 below, whatever our midline is. So what's that tell us, the 50? Amplitude. Remember, it could be plus 50 or minus 50. The amplitude is the absolute value. So it's 50. Amplitude. Whether we were looking at below or above, we're going to get 50. What else do we have to find? We have to find the value of B here. So the value of B is equal to 2 pi over P. So how is our animal population? What's the cycle? Low in the winter, high in the summer. What's going to be our cycle? How many months? 12 or a year, right? So we could say B is 12 pi divided by 1 year. So B is, 2 pi. So we got that part. So it looks like we're pretty good so far. We know we've got A is 50. We know B is 2 pi times T. We've got this moving, growing midline. So we just have to figure out which function are we going to use. Are we going to use sine, cosine, negative cosine? And this is really the part where it's up to you. Nobody told us how to measure T. I'll wait for you to copy this, so I'm talking over a lot of people writing. Your choice of where to start recording, you're out there in the field, when you start recording the population of these elks, up to you. If we start at its low point, which is the winter, so if we say let T equal 0 be the winter, when we're at our lowest point, then we know that's a negative cosine model. We start at our lowest, we go up through our midline, and then we go up to our maximum, right? Come back down, and then reach our lowest over a year. So we could use a negative cosine model. So now I'm going to put a negative in front of my 50 and a cosine here. So that would be the model I would use. Yes, but if you would have to put a shift in here, which I try to stay away from. Yeah. If you started in the summer, and you just 5, then it would just be 50 cosine. It would be the same thing. You wouldn't have to shift it. You'd only have to shift it if we were looking at the graph of this with your low point being at T0 and you wanted to go up to your maximum. Summer, yes. All right. So this is an example of a changing midline where your midline is growing exponentially. So before we were used to coming up with a function and all we had here was a single number. It was a constant. Our midline was called K or something, or D, I don't know, K I think we called it, right? So now it's an actual function. In this case, it's an exponential function. So that's the really big change from the models that we looked at earlier to the models we're looking at today. So changing midlines can be anything. And this is out of your textbook. Here's the one we just looked at. We should look at this on Desmos. You see how this midline is increasing and our population is still oscillating around that midline. This distance above and below the midline is still 50 in our case. Okay, but the actual average growth of, the average population of elk is growing. So let's take a look at this. Let's throw this into Desmos. I've started to really enjoy Desmos. It's just really quick and easy. GeoGebra is too, but I like the visuals, the colors. So what was this model here? Let's see what this looks like. Y equals -50. I think I can remember. If I can, I'll ask you. Thank you. 2, and then I have to put in pi. I think I can use t. Ooh, it's starting to look, wow. Right, just look at that. If that's just, that would be like a cosine function that's compressed, lots of cycles of cosine with a wicked amplitude from 50 to -50. So that's why it looks like almost straight lines here, right? And then what do we have to do? We have to add to that 2,000. Oh my God, I've lost it completely now. Times 1.04 raised to the t. I hope it graphs with t's instead of x's. Well, let's see what's going on. Well, first of all, where's my first value going to be? Way. Whoa, look at that. Isn't that cool? All right, here we go. Our first value is going to be up here at 2,000, right? So to really see this, I've got to play around with my axes. Just like on a calculator, graphing calculator, you have to change a window, right? So let's see. I don't really care what's going on before the winter months here or in years past. So I'm going to have my x-axis start at 0. 0, please. And let's see. We can go out a couple of years. Well, 2 pi. It was 1 year, so let's say 3 years. Oops, not 32 years, 3 years. And our y-axis, I guess we could start at 0. You see how my graph's changing already? My graph, let's say 0. And we know we want to go more than 2,000 elk. Let's say up to 2,400 elk. All right, let's see what that looks like. All right, it still doesn't look very nice. The heck? Oh, what's the steps there for my x-axis? Steps are what? 1 year. Yeah, I don't like that at all. Why is my y-axis going way down there? I had a nice picture of this in my office. Yeah, it's still not looking so hot. Let's see. We only want that to go to 20. See, it keeps changing on me, doesn't it? Maybe I'll have to go to GeoGebra. Yeah, it looks a little bit better. You can see. Let's put in the midline so we can see what's happening here. Let's put in the midline. So the midline itself was what? Yeah, y equals, because y equals 2,000 is going to be constant. We got a midline that's changing and shifting, right? So 2,000 times 1.04 raised to the t. Oh, okay. Thank you. There you go. You can see how you're oscillating above and below, but this midline is changing, so your maximum elk population, the oscillation, even though this distance is still only 50 elk, is getting bigger and bigger. So there's your oscillation, there's your shifting midline. Okay, and you can scroll this back as far as you want. That first one looked really wild. Let's see, we'll zoom out a little bit. You know, if we zoom out, it almost looks like you can't see anything, but there we go. So depending on what your need was for this model, you could get various points here. Okay. So here, this point you should know is where we start, right here. Is our lowest point, right? And then our maximum point is going to be right here, roughly, right? We cross the midline right there. It's a quarter of the way, half of the way, right? Roughly half the way. So I think you can get a sense of how this is increasing. And having your calculator or Desmos or GeoGebra handy to you as you do work through these really helps you to visually see these. And that's what's going on right here. Okay. Now this one has a midline that's linear. And your book does an example for you. And depending on how well you want to do in Math 107, you can either read your book and put these examples into your notes and work through them or not. This is example 3 in your textbook. And it deals with the number of tourists at a ski resort. So the only difference is instead of telling you how the population, in this case, number of tourists is growing at a constant percent, they're doing a constant rate of change, which is additive, like 200 each year or 200 each month, whatever the example is. So the little midline that you have at the end, this G of t, is just like an mx plus b model. Okay. So these are various, there's various examples of this in your book, more than this one that I've done. And again, I can only encourage you to read the book. You'll probably hear me say it 1,000 times. Any questions on how we came up with this model here? All right, let's see, what's next? Okay, so one of the little things your book does is it gives you data table versus a graph. So look, here's something we just looked at. Here's a sine function. And it's midline, I put the midline in front, doesn't matter, addition is commutative. And the midline is changing exponentially. So what do we need to find in order to figure out the model that fits this data? We need to find A, we need to find B, and we need to find C. So those of you who are from my 107 class know, because I've said this over and over again, we go from straight lines and you get y equals 2x plus b. And how do you find b? You take a point from your line, you plug it in. When you have a quadratic and you have your vertex and you're trying to find a, the leading coefficient, you take a point from your quadratic. You have an exponential function, blah, blah, blah. It's the same story. Okay? So each of these points is going to give you different information. Anytime you see an exponential, you hope that one of your x values is 0. Why? What does it give you right away when x is 0? A. Because when x is 0, b to the 0 is what number? 1. It's going to give you a value of a. So let's take each one of these points, 0, 6, and plug it in here and see what we get. All right, so we get y is 6. 6 equals a times b to the 0 plus c times the sine of pi over 2 times 0. So let's simplify this. 6 equals b to the 0 is just a nice fat 1. A plus c times sine of 0. And what's sine of 0? Thank you. Sine of 0 is 0. And what's c times 0? 0. So A is 6. So we use that first point. It's going to, in this particular case, it gives us 6. Yay! I can start to write home now. I'm getting really excited. All right, here we go. I've got my A all figured out. Check that off. All right, now let's look at our next point, see how much information that gives us. We have 1, 29. Okay, so my Y value is 29 when my X value is 1. But now I know what A is, so I'm going to put in 6 for A. B to the first plus C times the sine of pi over 2 times X, which is 1 in this case. So this is 29 equals 6 times B plus C. And what's pi over 2 times 1? It's pi over 2. And what's the sine of pi over 2? Sine of pi over 2? 1. So we get 29 equals 6B plus C. That has one equation with 2 unknowns. So we have to put that in reserve. That's like our reserve tank and our gas tank, right? We have to come back to this. But look, we're getting there. Now we only have 2 unknowns. Maybe we'll get one other equation that's going to now, and then we can come back to that. Okay. Question? Okay. So now we've used 120. Let's use our next point. Let's use 2, 96. So Y is 96 when X is 2. So what do I have? A is 6. X is 2, so that's the exponent of B. Plus C times sine of pi over 2 times X, which is 2. Oh, this is good, because I'm going to come back to one of those zeros again. Yay. And I get sine of pi here, and the sine of pi is a nice big 0. Yay! So this is going to help me solve for my value of B. So I get 96 equals 6 times B squared. I divide both sides by 6. 16 equals B squared. Isn't that lovely? B is plus or minus 4, but I'm looking at an exponential, and the one thing we know about our exponential function is that value of B is always positive. So we get B equals 4. Wow, now I've got B. So I can come up to my model here, and I can put 6 times 4 to the X. Yay. I'm almost there. Now it's time to go to my reserve gas tank, because my reserve gas tank didn't know B or C, but now I've put a little more gas in. B now is 4. And now I can solve for C, which is 5. So there's my model. So your book gives you 1 or 2 of these to do for homework. So good exercise. Now, the midline could be a linear equation, so it would be a lot easier to get. If you look at a data table and it's a straight line, you know how to find the equation of a straight line. I purposely chose an exponential because it was a little harder, just so that you would see one done in class. Any questions you can formulate at this point in your life about anything going on here?
I actually have a question. What if instead of using 1 year as period, we used 12 months?
Well, you'd get pi over 6, and so all that would happen is your cycle would happen in pi over 6. It would look the same. You would just know. So instead of it being like your 4 points being, you know, your max when you're back to 0 at your midline or wherever your midline is, and then your low point, and then your next point, instead it would be at 0, and then pi over 6 divided by 4, which is pi over 24, and then pi over 6 divided by 8. You know, you would just keep incrementing, which is yucky. I'd rather look at, 3 months, 6 months, 9 months, 12 months. Yeah, it's just easier. You can do it any way you want. All right, so, and remind me, Hazel, there's something later on I've got to talk to you. Remember when you said, oh, it looks like the Pythagorean theorem? Yeah, I found something that might help with that. Okay, so number 4. All right, so this is the little spring idea I was telling you about. And we already talked about this. When we looked at this in section 6.5, we were looking at simple harmonic motion. In other words, our spring was going on perpetually in time. Same amplitude, same max and min values, okay? But we know in real life that a spring doesn't oscillate and stay at the same height, high point and low point. It gets dampened down. So this is called damped oscillation, a damped harmonic motion. So let's take a look, and I think there's a nice way here to develop this idea. What we're going to do is we're going to develop the idea now of varying amplitudes. So we've looked at shifting midlines, now we're going to look at varying amplitudes. So again, this is one of the types of sinusoidal functions we could use. It could be a sine function, but we'll look at this. Notice now I'm back here, I've got e to the RT. I've switched my base to e instead of 1 plus r. And a little review for yourself. You can have 2 exponential functions like this. This was how we started off one of our 107 packets way back when we did exponential functions, modeling exponential functions. And if you look, oops, let me put t here so we have the same variable. If you look at this, t is the same in both. So b has to be the same as e to the r. B has to be the same as e to the r. And if let's suppose you know b, but you want to put it into a continuous growth model, you have to find r. In order to do that, r has to come out of the sky, so you take the natural log of both sides. And we know from our work with logs that the r comes down in front, and the natural log of v is just 1. So r will be the natural log of b. That's just a quick little thing that you can use. Okay. So, and I'll show you how to do this both ways. So let's consider a function that's said to have damped oscillation, which means we're going to start at some height, and let's say here's our midline, and we're not even going to go as low as we can before we start. That's the kind of thing we're going to try to now take a look at. It's almost like if your mouth was here, it's like a megaphone, right? Woo! It's going backwards from a megaphone. Okay. Sounds, the pitch, acoustic beats. I mean, there's tons and tons of applications for this. If you're musical at all, the number of cycles per second, okay, the frequency of sound of different notes, C versus C sharp. There's a change in the number of cycles per second. So there's oodles and oodles. We could spend the rest of our class just doing trig if we wanted. There's just so many examples out there. But you'll get a lot of this when you, those of you who are in EGR 114, right? How many, raise your hands? Okay, so you've already seen the, you got a problem where you were looking at the amplitude changing for a cosine function, right? You had, it was quiz number 4. Remember? She started you off with cosine? Okay, anyway. Yes, okay, all right. A little bit before you got here, though. Yeah. Well, Amy and I never knew that that course is supposed to mimic pre-calc, so hopefully the next time she teaches it, we'll put our curriculums together a little bit better. All right, so this particular type of function will oscillate with a decreasing amplitude. What the heck does that mean, with a decreasing amplitude? Do I have a picture of that here? Let's see. Thought I put one in. Okay. All right, so let's take a look at this on our calculators. What the heck? If you have a calculator, pull it out. Otherwise, you can just watch it up here. Okay, so I'm going to put this into the calculator. I'm going to use my standard window. Sometimes with trig functions, you want to use the z trig instead of the z standard, but this particular one, we're going to use our z standard window. Can't get this to come out. All right, then go back. I'll use this one. All right, so let's see, y equals, what's y going to equal here? 5e, so my e button's right above my natural log button because they're inverses of each other. E to the negative 0.05x. And then how do I get cosine 2x here so I'm not still up in the, is that going to work? It's not, I'm not up in the exponent, right? And how did I ensure that with these parentheses, right? Okay. I put them in. I'm parentheses like addicted, so yeah. So Zoom 6 tells us to use our standard window. Woo, baby. Here we go. Oh. All right, that's just 0 to 10. All right, so this piece right here in front of our, this piece, 5e to the negative 0.05x, if you notice, this all by itself, whoops, this all by itself is what kind of function right here? What kind of function is this? Exponential whaty? Exponential decay. So, exponential decay. So you would expect, hopefully, to see your peaks, your high points getting smaller and smaller and smaller, and your valleys, instead of being low, 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 they're not quite as low. They're increasing, your peaks are decreasing, but your valleys are increasing because your amplitude is changing. This right here is out in front of our cosine function. That's where we usually put the big capital letter A, right? That's where we usually put our amplitude. So let's get a picture of this right now. Where's my camera? Camera, thank you. And I've got to call this back up. And, yes, because it does stop. I guess I didn't do that right. It's not perpetual motion. Come on, please. Thank you. I just want to grab a little picture of this. All right. Into the clipboard, and I can paste it. So here is this function, this entire function. And as you can see, look what's happening to your peaks. They're decreasing from the x-axis, right? The distance from the x-axis is decreasing. And similarly, your valleys are not quite as low. They're increasing. So, what is the function of this right here? Let's take a look. We're now going to call 5e to the negative 0.05x. That's our amplitude. That's our amplitude. So if we really want to see, oh, I had to move that, didn't I? So there we go. If we really want to see what's going on, let's graph two more functions in our calculator. Let's graph this amplitude. Y equals 5e to the negative 0.05x and see what it does to our picture. So we'll keep this one right in there, and we're just going to throw in another function right below it. There we go. So 5e to the negative 0.05. Oops, forgot my x. X. Zoom 6. So there's my first function. Is that cool or is that cool? So here's your amplitude. Now look, each peak is getting smaller and smaller. It really wants, the cosine function wants to push it through that cap, that ceiling, but your exponential amplitude is dampening it down. It can't stretch up as high as it wants to. So each one of these points, if you were to throw it in here, would give you the amplitude. So what am I missing here? What other function am I missing to throw into my calculator? This is y2. What else can I put in here if I'm looking at amplitude? -5 e to the negative 0.05x. Because remember, your amplitude is the distance above and below your midline. We know that the amplitude's the absolute value. So let's now put that function in, which I think we can just do this. I think we can just say the opposite of y2. Now, how do I get y2? I can't remember. How do you get y2 back? I forgot. I want to be lazy. I don't want, you can just say the opposite of y2. Can you just do that? No. Okay, vars. Y vars. Yeah, thank you. So now I just say I want the opposite of y2. And let's graph that. Zoom 6. You will see all of this again in your physics class next year. There you go. No, it's exponential decay because of your R value. No. This, it's because of the negative, the two negatives. You know, the best thing to do, Hazel, to see what's going on is to do both of these functions, pick some values for x, y2, and y3. Okay? All right, so that's what we call varying amplitudes, oscillating amplitudes. It's really called damped harmonic motion, if you want the real fancy term. So here's two sinusoidal functions we could use. Notice this is from your book because you see on this first one they have b to the t, and here they have e to the rt. So how would I go back and forth? How could I get that same function we were just working on, but having it be b to a value rather than e to the negative 0.05? B equals e to the r. Yep. We know what r is. It's negative 0.05. So b is e to the negative 0.05. So if we wanted to write this function, we know that b to the x is the same as e to the r x. So x is done. So b is going to be e to the r, which is this. We expect b to be a number between 0 and 1 because it's exponential decay. So if we wanted to find the value for b, we just pull out our calculator. Second quit. We say e to the negative 0.05. So b is 0.95, whatever it was, 1, whatever. So if you now put this in for b, you'll get exactly the same function. Doesn't matter which base you use. You can go from one to the other. All right, so let's see. Do I have anything else for you? One more spring problem, and it's almost time to go. Here are the different amplitudes you can get. I'll just set this one up for you, and then I'll give you some time to work on the activities. A spring with a natural length of 20 inches is pulled back 6 inches and released. I think this one is also from your textbook. And I think here they're looking at a spring that's being pulled back from a wall. So it's being pulled, the natural spring itself is 20 inches. So that's your amplitude, right? 20 inches. It's being pulled back further from the wall, another 6. So at time t equals 0, your distance from the wall is 26 inches. So that's your maximum. So if we were starting to graph this, at time t equals 0, we'd be up at 20, we'd be 26 inches from the wall. This thing is now going to go back that way. It's going to pass its natural length at some point, which is 20 inches, and then it's going to go back, come back, and go back, and come back, and go back, and come back, and go back. But it's not going to come back to the same height. It's going to be decreasing. It's decreasing by 20% each second. Okay, 20% each second. So here we'll use our b to the t or b to the x model. So r is 0.20. Our base is 1 minus 0.20, which gives us 0.80. So the exponential model for this is what? Exponential decay. Okay. And so we get 0.8 to the t, and when t is 0, we're at 26, right? But that's our height. How are we going to do this? Let's see, we better go back up here. What do we use for A? Do we use anything here for A? What are we going to use for A? A is what? Do we use 20? What's the value for A? You wrote down 20? Oh, I wrote down. Oh, I'm sorry. I didn't mean to do that. I meant to say the natural. What's our value for our amplitude? This is 20 is the resting point. That's where we start. And we're going to compress it. How far did we compress it? Well, vertically, I would compress it. Horizontally, I would expand it. Okay. It's 6. That's our amplitude. Because at time t equals 0, we're at 6 centimeters above, right? Or out this way. Because we're going to be multiplying that all. That's the amplitude for this function. But what's our midline? What is our midline? What's our natural midline? 20. Okay, so look, even without the cosine function, we start at 20 at times t equals 0, right? This is going to be 6. 20 plus 6 brings us up to here. Right? Now we throw in a function. Since we're starting at our high point, we're going to start now with cosine. Only thing we got to figure out is b. That's it. B. So our period is what? We oscillate once every 2 seconds. So our period is 2 seconds. We oscillate once every 2 seconds. So B is 2 pi divided by 2, which is pi. So we begin 26 inches away from our wall, and then every single cycle, our peak's going to be smaller and smaller and smaller. I want to give you one other little bit of information. I mentioned this to you before. I called it omega, but now I want to be a little more specific. When we say that something repeats or oscillates once every 2 seconds, so one cycle every 2 seconds, do you see that that's the same as a half cycle per second, per 1 second? Okay. So the relationship between the period and your frequency, because this means you're going to go through one complete cycle in a half a second, is just they're reciprocals of each other. The frequency is 1/2. They're always got this inverse relationship. So it's 1/2 cycle per second. And I think your book uses you can use 1/2 hertz, H with a Z. That's another way to measure cycles per second. That's like when we're thinking about like AM and FM and sounds and stuff like that. That's your original midline, your natural length of your spring. This is your natural length of the spring. And from there, because our start hunter is with it being pulled back 6 inches, that's what you get right here as time t equals 0. All right. So I'm sorry I didn't give you time. I think I gave you 3 lesson activities. Since Friday's a little bit of a catch-up day, if you only get a couple of those done, it's okay. All right.